Liquids, Fluid Dynamics, Part 1. Objectives. Describe what determines the pressure of a liquid at any point. Explain what causes a buoyant force on an immersed or submerged object. Relate the buoyant force of an immersed or submerged object to the weight of the fluid it displaces. Describe what determines whether an object will sink or float in a fluid. Given the weight of a floating object, determine the weight of fluid it displaces. Describe how Pascal's principle can be applied to increase the force of a fluid on a surface. The big idea. In the liquid phase, molecules can flow freely from position to position by sliding over one another. A liquid takes the shape of its container. We live on the only planet in the solar system covered mostly by a liquid. Earth's oceans are made of H2O in the liquid phase. If Earth were a little closer to the sun, the oceans would turn to vapor. If Earth were a little farther away, most of its surface, not just its polar regions, would be solid ice. It's nice that Earth is where it is. In the liquid phase, molecules can flow freely from position to position by sliding over one another. A liquid takes the shape of its container. When does a liquid behave like a solid? Put 1 cup of cornstarch in a bowl. While stirring, add 1/2 cup of water. Try pushing on the mixture hard, then soft, then stir the mixture quickly, then very slowly. After pouring some of the liquid on the table, push on the puddle with the side of your hand. Try to pick up mixture. Once you have it in your hands, try to keep it in solid form by continually kneading it. Analyze and conclude. Observing. What is unusual about the mixture of cornstarch and water? Predicting. What do you suppose would happen if you were to try to play catch with the mixture? Making generalizations. Can you think of other substances that change from a liquid to a solid state, or vice versa when stressed? 19.1. Liquid pressure. A liquid in a container exerts forces on the walls and bottom of the container. To investigate the interaction between the liquid and a surface, it is useful to discuss the concept of pressure. Recall from Chapter 6 that pressure is defined as the force per unit area on which the force acts. The pressure that a block exerts on a table is simply the weight of the block divided by its area of contact. Similarly, for a liquid in a cylindrical container like the one shown in figure 19.1, the pressure the liquid exerts against the bottom of the container is the weight of the liquid divided by the area of the container bottom. 19.1. The liquid exerts a pressure against the bottom of the container just as the block exerts a pressure against the table. We'll ignore for now the additional atmospheric pressure. The pressure of a liquid at rest depends only on the gravity and the density and depth of the liquid. Density, how much liquid weighs and thus how much pressure it exerts, depends on its density. Consider 2 identical containers, one filled with mercury and the other filled to the same depth with water. For the same depth, the denser liquid exerts more pressure. Mercury is 13.6 times more dense than water. So, for the same volume of liquid, the weight of mercury is 13.6 times the weight of water. Thus, the pressure of mercury on the bottom is 13.6 times the pressure of water. Discover. How does depth affect blood pressure? 1. Note how the veins on the back of your hands stand out when you bend over so your hands are the lowest part of your body. 2. Note the difference when you hold your hands above your head. 3. Think. Why is your blood pressure measured in your upper arm level with your heart? Think. A brick mason wishes to mark the back of a building at the exact height of bricks already laid at the front of the building. How can he measure the same height using only a garden hose and water? To measure the same height, the brick mason can extend a garden hose that is open at both ends from the front to the back of the house and fill it with water until the water level reaches the height of bricks in the front. Since water seeks its own level, the level of water in the other end of the hose will be the same. Depth. For any given liquid, the pressure on the bottom of the container will be greater if the liquid is deeper. Consider the two containers in figure 19.2a. The liquid in the first container is twice as deep as the liquid in the second container. As with the two blocks on top of each other in figure 19.2b, liquid pressure at the bottom of the first container will be twice that of the second container. The pressure of a liquid at rest does not depend on the shape of the container or the size of its bottom surface. Liquids are practically incompressible, so except for changes in temperature, the density of a liquid is normally the same at all depths. Figure 19.2. Liquid pressure depends on depth. A. The liquid in the first container is twice as deep, so the pressure on the bottom is twice that exerted by the liquid in the second container. B. Similarly, the two blocks exert twice as much pressure on the table as one block. The pressure created by a liquid is pressure due to liquid equals density times G times the depth, or P equals rho GH. At a given depth, a given liquid exerts the same pressure against any surface, the bottom or sides of its container, or even the surface of an object submerged in the liquid to that depth. The pressure a liquid exerts depends on its density and depth. If you press your hand against a surface and somebody else presses against your hand in the same direction, then the pressure against the surface is greater than if you pressed alone. Likewise, with the atmospheric pressure that presses on the surface of a liquid, the total pressure of a liquid then is density times G times depth plus the pressure of the atmosphere. When this distinction is important, we will use the term total pressure. Otherwise, our discussions of liquid pressure refer to pressure in addition to the normally ever-present atmospheric pressure. You'll learn more about atmospheric pressure in the next chapter. Volume. It may surprise you that the pressure of a liquid does not depend on the amount of liquid. Neither the volume nor even the total weight of liquid matters. For example, if you sampled water pressure at 1 meter beneath the surface of a lake and 1 meter beneath the surface of a small pool, the pressures would be the same. The dam that must withstand the greater pressure is the dam with the deepest water behind it, not the most water, as shown in figure 19.3. The fact that water pressure depends on depth and not on volume is nicely illustrated with the Pascal's vases, shown in figure 19.4. Liquid pressure equals rho GH. That little symbol is a Greek letter rho. Figure 19.3, the water pressure is greater at the bottom of the deeper lake, not the lake with more water. The dam holding back water twice as deep must withstand greater average water pressure, regardless of the total volume of water. 19.4. The pressure of a liquid is the same at any given depth below the surface, regardless of the shape of the container. Note that the water's surface in each of the connected vases is at the same level. This occurs because the pressures at equal depths beneath the surface are the same. At the bottom of all four vases, for example, the pressures are equal. If they are not, liquid would flow until the pressures were equalized. This is why we say water seeks its own level. At any point within a liquid, the forces that produce pressures are exerted equally in all directions. For example, when you are swimming underwater, no matter which way you tilt your head, you feel the same amount of water pressure on your ears. When the liquid is pressing against the surface, there is a force from the liquid directed perpendicular to the surface as shown in figure 19.5a. If there is a hole in the surface, the liquid initially will move perpendicular to the surface. 19.5. The force in a liquid produces pressure. A. The forces against the surface add up to a net force that is perpendicular to the surface. B. Liquid escaping through holes initially moves perpendicular to the surface. Gravity, of course, causes the path of the liquid to curve downward, as shown in figure 19.5b. At greater depths, the net force is greater, and the velocity of the escaping liquid is greater. Concept check. What determines the pressure of a liquid? 19.2. Buoyancy. If you have ever lifted a submerged object out of water, you are familiar with buoyancy. Buoyancy is the apparent loss of weight of objects when submerged in a liquid. It is a lot easier to lift a boulder submerged on the bottom of a riverbed than to lift it above the water's surface. The reason is that when the boulder is submerged, the water exerts an upward force that is opposite in direction to gravity. This upward force is called the buoyant force. The buoyant force is the net upward force exerted by a fluid on a submerged or immersed object. To understand where the buoyant force comes from, look at figure 19.6. Figure 19.6. The upward forces against the bottom of a submerged object are greater than the downward forces against the top. There is a net upward force, the buoyant force. The arrows represent the forces within the liquid that produce pressure against the submerged boulder. The forces are greater at greater depths. The forces acting horizontally against the sides cancel each other, so the boulder is not pushed sideways. But the forces acting upward against the bottom are greater than those acting downward against the top because the bottom of the boulder is deeper. The difference in upward and downward forces is the buoyant force. When the weight of a submerged object is greater than the buoyant force, the object will sink. When the weight is less than the buoyant force, the object will rise to the surface and float. When the weight is equal to the buoyant force, the submerged object will remain at any level like a fish. To further understand buoyancy, it helps to think more about what happens when an object is placed in water. If a stone is placed in a container of water, the water level will rise as shown in figure 19.7. Water is said to be displaced or pushed aside by the stone. A little thought will tell us that the volume, that is, the amount of space taken up, or the number of cubic centimeters, of water displaced is equal to the volume of the stone. A completely submerged object always displaces a volume of liquid equal to its own volume. As figure 19.8 shows, this gives us a good way to determine the volume of an irregularly shaped object. When an object is submerged, it displaces a volume of water equal to the volume of the object itself. 19.8. When an object is submerged in a container that is initially brim full, the volume of water that overflows is equal to the volume of the liquid itself. Simply submerge it in water in a measuring cup and note the apparent increase in volume of water. That increase is equal to the volume of the submerged object. You'll find this technique handy whenever you want to determine the density of things like rocks that have irregular shapes. Notes: stick your foot in a swimming pool and your foot is immersed. Jump in and sink below the surface, and immersion is total. You're submerged. Concept check. What determines if an object will sink or float? 19.3. Archimedes' principle. Archimedes' principle describes the relationship between buoyancy and displaced liquids. It was discovered in ancient times by the Greek philosopher Archimedes, 3rd century BCE. Archimedes' principle states that the buoyant force on an immersed object is equal to the weight of the fluid it displaces. Archimedes' principle is true for liquids and gases, which are both fluids. Immersed means either completely or partially submerged. Think. A 1 liter container filled with mercury has a mass of 13.6 kilograms and weighs 136 newtons. When it is submerged in water, what is the buoyant force on it? Think. Answer. The buoyant force equals the weight of 1 liter of water, about 10 newtons, because the volume of displaced water is 1 liter. For example, if we immerse a sealed 1 liter container like the one shown in figure 19.9 halfway into water, it will displace half a liter of water and be buoyed up by the weight of half a liter of water. If we immerse it all the way, submerge it, it will be buoyed up by the weight of a full liter of water, 10 newtons. Unless the completely submerged container becomes compressed, the buoyant force will equal the weight of 1 liter of water at any depth. Why? Because the container will displace the same volume of water and hence the same weight of water at any depth. The weight of this displaced water, not the weight of the submerged object, is the buoyant force. A 300-gram brick weighs about 3 newtons in air. 19.9. A liquid of water occupies 1,000 cubic centimeters, has a mass of 1 kilogram, and weighs 10 newtons. Any object with a volume of 1 liter will experience a buoyant force of 10 newtons when fully submerged in water. Suppose, as shown in figure 19.10, the brick displaces 2 newtons of water when it is submerged. The buoyant force on the submerged brick will also equal 2 newtons. The brick will seem to weigh less underwater than above water. The apparent weight of the submerged object is its weight in air minus the buoyant force. In the water, the block's apparent weight will be 3 newtons minus the 2 Newton buoyant force, or 1 newton. So the block appears lighter underwater by an amount equal to the weight of water, 2 newtons, that has spilled into the smaller container. For any submerged block, the upward force due to water pressure on the bottom of the block minus the downward force due to water pressure on the top equals the weight of the liquid displaced. As long as the block is submerged, depth makes no difference. Why? Figure 19.10. A brick weighs less in water than in air. The buoyant force on the submerged brick is equal to the weight of water displaced. Because although there is more pressure at greater depths, the difference in pressure on the bottom and top of the block is the same at any depth as shown in figure 1911. Whatever the shape of a submerged object, the buoyant force equals the weight of liquid displaced. Concept check. What does Archimedes' principle state? Figure 1911, the difference in the upward force and the downward force acting on the submerged block is the same at any depth. Think. A solid block is held suspended beneath the water in the three positions A, B, and C, shown in figure 1911. In which position is the buoyant force on it greatest? The buoyant force is the same on all three positions because the amount of water displaced is the same in A, B, and C. Think. A stone is thrown into a deep lake. As it sinks deeper and deeper into the water, does the buoyant force on it increase, decrease, or remain unchanged? The volume of displaced water is the same at any depth. Water is practically incompressible, so its density is the same at any depth, and equal volumes of water weigh the same. The buoyant force on the stone remains unchanged as it sinks deeper and deeper. 19.4. Does it sink or does it float? We have learned that buoyant force on a submerged object depends on the object's volume. A smaller object displaces less water, so a smaller buoyant force acts on it. A larger object displaces more water, so a larger buoyant force acts on it. The submerged object's volume, not its weight, determines buoyant force. A misunderstanding of this idea is at the root of a lot of confusion that you or your friends may have about buoyancy. So far, we focused on the weight of displaced fluid, not the weight of the submerged object. Now we consider its role. Discover. How does displacing water affect the reading on a scale? Place a beaker of water on a scale and note the reading. 2. What do you think will happen to the reading if you lightly touch the surface of the water with your finger? What do you think will happen to the reading if you push the water downward? And 4. Think. How does displacing some water affect the depth of the water? How does the depth of the water affect the pressure on the bottom of the beaker? How does the pressure affect the reading on the scale? Whether an object sinks or floats or does neither depends on its buoyant force up and its weight down, how great the buoyant force is compared with the object's weight. Careful thought will show that when the buoyant force exactly equals the weight of a completely submerged object, then the object's weight must equal the weight of displaced water. Since the volumes of the object and of displaced water are the same, the density of the object must equal the density of the water. Look at figure 1912. The fish is at one with the water. It doesn't sink or float. The density of the liquid equals the density of the water. If the fish were somehow bloated up, it would be less dense than water and would float to the top. Figure 1912. The wood floats because it is less dense than water. The rock sinks because it is more dense than water. The fish neither rises nor sinks because it has the same density as water. If the fish swallowed a stone and became more dense than water, it would sink to the bottom. Sinking and floating can be summed up in 3 simple rules. An object more dense than the fluid in which it is immersed sinks. An object less dense than the fluid in which it is immersed floats. An object with density equal to the density of the fluid in which it is immersed neither sinks nor floats. From these rules, what do we say about people who, try as they may, cannot float? They're simply too dense. To float more easily, you must reduce your density. Since density is mass divided by volume, you must either reduce your mass or increase your volume. Taking in a lungful of air can increase your volume temporarily. A life jacket does the job better. It increases volume while adding little to your mass. The density of the submarine is controlled by the flow of water into and out of its ballast tanks. In this way, the weight of the submarine can be varied to achieve the desired average density. A fish regulates its density by expanding or contracting an air sac that changes its volume. Think. We know that if a fish makes itself more dense, it will sink. If it makes itself less dense, it will rise. In terms of buoyant force, why is this so? Let's see. When the fish increases its density by increasing its volume, it displaces less water, so the buoyant force decreases. When the fish decreases its density by expanding, it displaces more water, and the buoyant force increases. The fish can move upward by increasing its volume, which decreases density, and downward by contracting its volume, which increases its density. Notes: cans of diet drinks float in water, while sugar drinks sink. Diet drinks are less dense than water. Sugar drinks are denser than water. A crocodile increases its density when it swallows stones. From 4 to 5 kilograms of stones have been found lodged in the front part of the stomach in large alligators. With its increased density, a crocodile like the one in figure 1913 swims lower in the water and exposes less of itself to its prey. Concept check. What are the 3 rules of sinking and floating? 1913, the crocodile on the left is less dense than the crocodile on the right because its belly is not full of stones. 1905, flotation. Primitive peoples made their boats of wood. Could they have conceived of an iron ship? We don't know. The idea of floating iron might have seemed strange. Today, it is easy for us to understand how a ship made of iron can float. Consider a solid 1-ton block of iron. Iron is nearly 8 times as dense as water, so when it is submerged, it will displace only 1/8 ton of water. The buoyant force will be far from enough to keep it from sinking. Suppose we reshape the same iron block into a bowl shape, as shown in figure 1914. The iron bowl still weighs 1 ton. If you lower the bowl into a body of water, it displaces a greater volume of water than before. 1914, a solid iron block sinks, while the same block shaped to occupy at least 8 times as much volume floats. Floating mountains link to geology. Just as most of the floating iceberg is below the water's surface, most of the mountain is below ground level. Mountains float too. About 15% of a mountain is above the surrounding ground level. The rest extends deep into the earth, resting on the dense semi-liquid mantle. If we could shave off the top of an iceberg, the iceberg would be lighter and float higher. Similarly, when mountains erode, they float higher. That's why it takes so long for mountains to weather away. As the mountain wears away, it floats higher, pushed up from below. When a mile of mountain erodes away, 85% of it comes back. The deeper a bowl is immersed, the more water is displaced, and the greater is the buoyant force exerted on the bowl. When the weight of the displaced water equals the weight of the bowl, it will sink no farther. It will float because the buoyant force now equals the weight of the bowl. This is an example of the principle of flotation. The principle of flotation states that a floating object displaces a weight of fluid equal to its own weight. 1916 demonstrates a simple experiment you can do to test the principle of flotation. Every ship must be designed to displace a weight of water equal to its own weight. Figure 1916, a floating object displaces a weight of liquid equal to its own weight. Thus, a 10,000-ton ship must be built wide enough to displace 10,000 tons of water before it sinks too deep below the surface. The canoe in figure 1915 and the ship in figure 1917 float lower in the water when they are loaded. The weight of the load equals the weight of the extra water displaced. Think about a submarine beneath its surface. If it displaces a weight of water greater than its own weight, it will rise. If it displaces less, it will go down. Notes: only in the special case of floating does the buoyant force acting on an object equal the object's weight. Figure 1915, the weight of the floating canoe equals the weight of the water displaced by the submerged part of the canoe. 1917, the same ship is shown empty and loaded. The weight of the ship's load equals the weight of extra water displaced. If it displaces exactly its weight, it will remain at constant depth. Water has slightly different densities at different temperatures, so a submarine must make periodic adjustments as it moves through the ocean. As the next chapter shows, a hot air balloon obeys the same rules. Concept check. What does the principle of flotation state? 1906, Pascal's principle. Push a stick against a wall and you can exert force at a distance. Interestingly enough, we can do the same with a fluid. Whenever we change the pressure in one part of a liquid, this change is transmitted to other parts. For example, if the pressure of city water is increased at the pumping station by 10 units of pressure, the pressure elsewhere in the pipes of the connected system will be increased by 10 units of pressure when water is not flowing. Pascal's principle describes how changes in a pressure are transmitted in a fluid. Notes: although water covers 2/3 of the planet, oceans are least understood ecosystems and likely the most at risk. Pascal's principle states that changes in pressure at any point in an enclosed fluid at rest are transmitted undiminished to all points in the fluid and act in all directions. Pascal's principle was discovered in the 17th century by Blaise Pascal, for whom the SI unit of pressure is named. Pascal's principle is employed in a hydraulic press. If you fill a U-shaped tube with water and place pistons at either end, as shown in figure 1918, pressure exerted against the left piston will be transmitted throughout the liquid and against the bottom of the right piston. 1918. The force exerted on the left piston increases the pressure in the liquid and is transmitted to the right piston. The pistons are simply plugs that fit snugly but can freely slide inside the tube. The pressure the left piston exerts against the water is exactly equal to the pressure the water exerts against the right piston if the levels are the same. This is nothing to get excited about, but suppose you make the tube on the right side and use a piston of larger area, then the result is impressive. In figure 1919, the piston on the left has an area of 1 square centimeter, and the piston on the right has an area 50 times as great, 50 square centimeters. Suppose there is a 1 Newton load on the left piston, then an additional pressure of 1 Newton per square centimeter, 1 Newton per square centimeter, is transmitted throughout the liquid and up against the larger piston. 1919, a 1 Newton load on the left piston will support a 50 Newton on the right piston. Remember the equation for Pascal's principle. Here is where the difference between force and pressure come in. The additional pressure of 1 Newton per square centimeter is exerted against every square centimeter of the larger piston. Since there are 50 square centimeters, the total extra force exerted on the larger piston is 50 newtons. Thus, the larger piston will support a 50 Newton load. This is 50 times the load on the smaller piston. This is quite remarkable, for we can multiply forces with such a device. A 1 Newton input, 50 newtons output. By further increasing the area of the larger piston or reducing the area of the smaller piston, we can multiply forces to any amount. Pascal's principle underlies the operation of the hydraulic press. The hydraulic press does not violate energy conservation, for the increase in force is compensated for by an increase in distance moved. When the small piston in the last example is moved downward 10 centimeters, the large piston will be raised only 1/50th of this, or 0.2 centimeters. Very much like a mechanical lever, the input force multiplied by the decrease it moves is equal to the output force multiplied by the distance it moves. The hydraulic press is a machine much like those discussed in section 9.8. Pascal's principle applies to all fluids, gas and liquids. A typical application of Pascal's principle for gases and liquids is the automobile lift shown in figure 1920. The automobile lift is in many service stations. 1920, the automobile lift in a service station is an application of Pascal's principle. A low pressure exerted over a relatively large area produces a large force. Think, as the automobile in figure 1920 is being lifted, how does the change in oil level in the reservoir compare with the distance the automobile moves? The car moves up a greater distance than the oil level drops, since the area of the piston is smaller than the surface area of the oil in the reservoir. Compressed air exerted pressure on the oil in an underground reservoir. The oil, in turn, transmits the pressure to the cylinder, which lifts the automobile. The relatively low pressure that exerts the lifting force against the piston is about the same as the air pressure in the tires of the automobile, because a low pressure exerted over a relatively large area produces a considerable force. It's important to note that the oil surface doesn't act like the input pistons of figures 1918 and 1919. Whatever air pressure the compressor supplies to the reservoir, regardless of the oil's surface area, is transmitted through the oil to the piston that raises the car. What does Pascal's principle state? Summary: liquids. The pressure of a liquid at rest depends only on gravity and the density and depth of the liquid. When the weight of a submerged object is greater than the buoyant force, the object will sink. When the weight is less than the buoyant force, the object will rise to the surface and float. Archimedes' principle states that the buoyant force on an immersed object is equal to the weight of the fluid it displaces. Sinking and floating can be summed up in three simple rules. An object more dense than the liquid in which it is immersed sinks. An object less dense than the fluid in which it is immersed floats. An object with density equal to the density of the fluid in which it is immersed neither sinks nor floats. The principle of flotation states that a floating object displaces a weight of fluid equal to its own weight. Pascal's principle states that changes in pressure at any point in an enclosed fluid at rest are transmitted undiminished to all points in the fluid and act in all directions.